Welcome back now to the 36th lecture of the course. So we are nearing the completion. I'm not very sure how you have enjoyed, but I really hope that you have enjoyed the course and you have been following the lectures and have submitted the assignments. And I would really like all of you to sit for the examination, get a certificate. And I mean, it's very simple. If you have just heard the courses, the lectures, and gone through the whatever material that we have uploaded, I'm sure you will do very well in the examination. I never ask questions which I have not taught, and therefore I just check how you are able to grab whatever I have taught. So I really hope to see all of your names appearing in the answer scripts that we are going to evaluate in a few weeks time from now. Anyway, of course you are. The other thing is that you can always send in the discussion forum or through the form of email any specific suggestion that you may want to have, specific improvement you would like to have. Of course, please do not forget that the framework does not allow us to interact inside a class, which is of course the most sought after and well desired way of teaching. At least I feel it that way, but at least you get a glimpse of what the subject is and what we do and stuff like that. So considering the limitation of this framework, I am sure you have enjoyed the course. Anyway, coming back to topic, we have been talking about spontaneous instability and dewetting of ultra thin films, and we have looked into the issues from somewhat theoretical details, and now we understand that it is essentially one can look into the magnitude and the sign of, let's say, a parameter like effective interface potential, or let's say the disjoining pressure, and one can sort of have a qualitative idea whether about the stability of the film. Of course, the entire theoretical framework that we have discussed so far is considering van der Waals forces, because Hamarkar constant is a constant that is defined only for van der Waals interaction. So you can always ask what is going to happen in real situations, because we have even neglected the polar interactions. Well, it turns out that most of the polymers, until and unless you actually take a semi-crystalline polymer or something like that, or a conjugated polymer to be more precise, they lack the polar interactions, and therefore their behavior, it has been surprisingly found, in fact, that is rather well captured based on a theory or formulation that only considers van der Waals interaction. Of course, the other important aspect, since we are using a polymer, so what we gain is that polar interaction is mostly absent in the system. That is true, but what is really lacking in the formulation that we have talked so far, and that's where actually deviations in experiments do come in, I must admit, that is we are also neglecting the steric interactions. And now you should all understand that for long chain polymer molecules, the entanglement is indeed there, steric interactions is there, or are there, which are neglected in whatever we have taught so far. In fact, honestly speaking, considering steric interaction and issues like that is still at the research level. I mean, there is a lot of work going on, but it will probably take some more time before these topics make their way into textbooks. The other issue is that I did not teach, particularly because of the paucity of the time, as well as due to I did not want to make the course really very heavy and complicated. I did not teach the hydrodynamics of thin film, which is even in fact a rather simple approach. One can just look into the Navier-Stokes equation and do a linear stability analysis. And in fact, one of the resources that I have referred to, that is my NPTEL lectures and the web material. You can find it there. It's not included in this course, but any of you who is interested, who want to study it further, you can always do that. You will find there that viscosity, the polymer viscosity, the liquid viscosity has been considered similar to that of a Newtonian fluid. And that's also not correct, because of the entanglement effects and this presence of the long chain molecules, polymer melts in fact exhibit significant amount of nonlinear behavior, non-Newtonian behavior, and those things needs to be incorporated in the development of more precise and accurate theory. But one thing is pretty convincing, that whatever be the precise rheological model, that in fact does not affect the stability, that sort of alters the dynamics, evolution sequence, and some recent experimental studies of course suggest that they might also alter the morphology during evolution. So for example, I briefly mentioned that we talked about this rim formation around a growing hole, and depending on the level of viscoelasticity, so if issue is that you are looking at a dewetting of a rather viscous film, the profile of the outer periphery of the rim, or the rim profile, is rather symmetric. So what it means is, for a viscous film, the rim cross section is symmetric. That is, it's something like this. However, if you are looking at dewetting of a strongly viscoelastic film, you know you can choose the molecular weight in such a way that the film exhibits significant level of viscoelasticity. The rim profile often turns out to be something like this. I am not going into the detail but why it happens, but this has been experimentally observed, and so this is how the viscoelasticity affects the evolution morphology in addition to the dynamics. But what we will focus in this lecture is something different. See, we are now all familiar with this particular picture, which is essentially the key evolution sequences of a polymer film. So you have a flat film, and what I had hinted, that one fascinating aspect is you only spin coat a flat film and do nothing. All you do is, these films behave like solid at room temperature, because their glass transition temperature is above room temperature. It's, if it is a polystyrene or a PMMA film, in fact the TG is close to 100 degrees centigrade. So at room temperature, irrespective of the wettability of the substrate, sign of the effective interface potential, you are not going to see any dynamics. But all you have done in order to trigger this evolution sequence is to heat up the film, or to expose it to its solvent vapor. There are subtle differences, I must admit, between solvent vapor exposure and heating up of the film. I don't want to go into all of them, but one of the major things that you may want to consider is that, though you consider, despite you considering the fact that there is coefficient of thermal expansion, the expansion in a polymeric material is not very large. Therefore, after heating, when the film is about to dewet, its thickness is roughly of the same order as that of the initial thickness of the film. But when you do the second approach, that is, you do a solvent vapor exposure, I have already mentioned that what happens is the solvent molecules enter into the film matrix and they swell. So one immediate difference that you can observe is that in the latter case, at the point when the film is about to dewet, it's actually thicker than its original thickness. Anyway, for this course, again, yesterday in one of the earlier lectures I mentioned that if I'd like to talk about many more detailed aspects of dewetting if I take a dedicated course on dewetting. Let me see, depending on the feedback and response of this particular course, that I will decide. So if I ever take that, I will probably discuss all this in greater detail. However, what is important is, irrespective of the precise route, is this form of spontaneous instability is undesirable as a coating, and I already mentioned that research work is already going on to suppress this instability, and one of the preferred route is in fact to add nanoparticles very small proportion. So what happens is in fact very exciting. Instead of a pure homopolymer film, now you actually have a nanocomposite thin film. You have these nanoparticles, and these nanoparticles exhibit dynamics with respect to the polymer chain. In fact, based on the entropic interactions, it has been shown by several workers that these nanoparticles choose to migrate to the liquid substrate interface, because what happens is the polymer chains, which are again the long chain molecules, their rotational entropy sort of gets truncated because of the fact that they are sticking, the ones that are sticking to the substrate. So if a polymer molecule is released from the substrate and is replaced by a nanoparticle, in fact that polymer chain gains in conformational entropy, and that's how the system is thermodynamically favored, right? But again, that is a topic I will not touch upon. But what is more interesting is that what I was trying to highlight and got deviated is that you started off with a flat film and you are creating some nano and mesoscale structures. So in fact, instability, spontaneous instability in a way is a route for nanofabrication or novel mesoscale fabrication with soft materials. The limitation is we have seen how beautiful the structures you can make while we were studying soft lithography and photolithography, and these structures are random and isotropic. So such structures are often of no use. So significant research is in fact aimed at aligning these structures. Okay, you cannot really take a flat film on a flat substrate and align it. In fact, you need to do something, and that something turns out to be, there are two very popular approaches and some not so popular research level approaches which people have tried out. In fact, those approaches are to use a patterned substrate, and that patterned substrate in fact includes, you can either use a chemically patterned substrate or you can use a topographically patterned substrate. And so what you do is, in a nutshell, flat smooth film is what we have talked so far. You either heat up or expose to solvent vapor, and you get some random structures. In contrast, what you do is, in order to align them, you would like to take either a chemically patterned substrate or a topographically patterned substrate. I am drawing the film on this topographically patterned substrate a bit later. Let us consider a chemically patterned substrate. So now you see, you seamlessly know in fact how to perform these experiments. How do you make these chemically patterned substrates? You simply make them by microcontact printing. And therefore, what are these chemical patterns? You typically have chemical patterns with alternating domains of hydrophilic or hydrophobic areas. And now you also know what is hydrophobic and hydrophilic. In fact, with respect to water, typically hydrophobic patches will have low surface energy, hydrophilic patches will have high surface energy. So that in fact translates most likely to the fact that the spreading coefficient on one of the patches is in fact going to be negative, in fact probably over the hydrophobic patches, and the local spreading coefficient over the hydrophilic patches are going to be positive. So, variation to be different. And do I really tell you more? The answer is no. So, suppose if these are the areas where the spreading coefficients are negative, let us say these are the hydrophobic patches, thermodynamically the film is unstable over here, whereas here if the spreading coefficients are positive or they have much lower value, in principle the film is stable over these patches. So, what are you essentially doing? You have a film which is periodically unstable over certain locations, and essentially you would like the film. Now, what you are doing is you are specifying a heterogeneity in the form of the substrate. In fact, it is a chemically heterogeneous surface. You want the film to rupture over the hydrophobic areas, and that is exactly what people have done. People have taken micro contact printed surfaces. So, these are in fact some simulation results, excellent simulation results, and you can create or you can achieve what is known as templating, that is whatever is the geometry of the chemical patterns that gets reflected in the topography of the dewetted film. So, under perfect templating, this is what the original papers talked about. So, if this is please understand these are chemically patterned patches. So, topographically they will be roughly smooth. So, you take this is the substrate, let us say red corresponds to low surface area domains, and you take the film on top of that. So, let us consider we are taking a cross sectional view we are talking about. So, this is the film. What you would like to expect under appropriate condition, and what are the conditions? Let us not get into that. You can look into tons of wonderful work by Kajri Kargupta and Ashutosh Sharma around 2000 to 2003. That's the area they have lots of top class publications on this particular area, and you would expect, in fact, if these are the low surface area domains, so you would expect that after dewetting the film profile would be something like this. Why? Because I hope the picture is clear to you, because over these red zones it is a low surface area patches, and therefore it is likely that the film will rupture over these areas. So, you essentially probably the picture got a bit clumsy. You would expect the film to however, simulation and subsequent experiments also shows that of course, this first let me discuss this. that there is a there are a whole lot of parameters that affect the ordering. Please do not understand that the moment you take a chemically patterned surface you are going to get order. That's not going to be possible, because film thickness is a critical parameter. Film thickness also gives you the natural length scale of instability, the periodicity of the patches, the duty ratio of the patches. The duty ratio essentially is a term which is like, you have, let's say, this alternating patches at a periodicity of, let's say, lambda p, but you see you can also have structures like this, same periodicity, but here the ratio or here the width of the let's say hydrophobic patches is more as compared to that of the hydrophilic patch. So, duty ratio is something like a ratio of, let's say, L hydrophobic minus L hydrophilic, and for this type of a surface, of course, you can immediately figure out that summation of this phobic plus philic is going to give lambda p, and most of the structures of the gratings we consider, because that's the easiest to fabricate. Often we have this ratio is equal to 1 for a surface like this. So, this ratio is often referred to as the duty ratio. You can just check out the net what is the classical definition. So, film thickness, periodicity of the structures. So, let me just make a quick list: film thickness, periodicity of the structures, duty ratio, difference in the wettability, of the two patches. That is an important parameter. So, if you have lambda 1 and lambda 2 over here, the magnitude of lambda 1 and lambda 2 in fact matters. There is a beautiful paper published something around 2007 or 8, which in fact shows that there is a critical value of this lambda 1 minus lambda 2, below which the effect of ordering gets completely distorted. Anyway, so this is a beautiful area. I must also mention a wonderful story, and which highlights the strength of simulation related or theoretical work. This entire work, as I mentioned, these are the two pioneers in this field, and both are from India, at Kanpur. The entire development was first simulated and theoretically predicted, and experiments subsequently followed. So, this is what good theory can in fact do. This is how good theory can enrich science. Okay, moving on, what is the other approach? So, the other approach, so one is pattern directed dewetting, but to use a chemically patterned substrate, and in fact this has received more attention. The second option is to use a topographically patterned substrate. Now, and you see we already have some AFM images which actually shows that these dewetted droplets, which were random, can be beautifully ordered on a topographically patterned substrate. So, for example, if you take this particular figure on the right side, each one of these tiny droplets are dewetted droplets, and the cross pattern is a soft lithographically fabricated template. But we talk about this topographically patterned substrate. In fact, I am going to spend some time on this, but does it ring any question on your mind as to why I have not drawn the film on top of the topographically patterned substrate? It is in fact a very good question to ask, and the answer is this question. The answer to this is non-trivial, because so far we have only considered or always considered on a smooth flat substrate, which, and therefore in the context of dewetting, even in the context of chemical pattern directed dewetting, the initial thickness of the film is uniform. But if you look at this condition, is it possible for you to get an uniform film thickness if you spin coat? And this is not a hypothetical problem, because one thing I'd like to remind you that in photolithography, the spin coating is not popular because you would like to do soft lithography or dewetting. Spin coating is popular because photolithography extensively requires spin coating. And in photolithography, when we talked about these concepts of mask aligner and things like that, you have seen that you might have to coat several layers, or you might have to perform photolithography several times and over a pre-existing pattern. So essentially the question of spin coating on a pattern substrate is non-trivial, and I am sorry to say fundamental understanding was rather poor, which sort of got corrected very recently. However, initial pattern directed dewetting experiments on topographic pattern surfaces, people were little scared to, or honestly speaking nobody knew how exactly this variation takes place on a topographically patterned substrate, the film thickness variation. So what was done was, very painstakingly the samples were prepared by coating it on a flat uniform silicon wafer or a mica sheet, and then floating it on water, and then transferring it onto the topographically patterned substrate. So this way you ensure that your film thickness at least remains constant or uniform. It was also shown that the way you transfer, that is the way you recapture, so the this is sort of a cartoon that gives you an idea of what was done. This is a layer of water, you take the film, you need to have really very good hands. So this was coated on a flat surface, then you float it on water. There is every possibility that there will be a lot of wrinkles, those are going to spoil your samples, and you capture it with a pattern surface. I will repeat it. So you coat it by spin coating on a smooth surface, then you float it on water, and then you recapture it with another topographically patterned substrate. So this was how initial samples for these experiments were created, and it was also shown that depending on the angle at which you pick up your sample, you can have two different initial configurations. So if you picked up your substrate vertically, you actually get a completely conformal adhesion of the film with respect to the substrate. In contrast, if you pick it up horizontally, you sort of get a film morphology which is hanging, which is in contact with only the protrusions and hanging over the other areas. So depending on how you prepare your film, you could either lead to this and lead to this. We're running out of time in this particular lecture, so I will start my discussion for the subsequent lecture, which will also continue on pattern directed dewetting from here. Thank you.